What's going on, everybody? I got a tennis ball right here. I'm going to be throwing it against this wall. All right, so let's say that this tennis ball has like 200 grams and I throw it about 2 meters per second. Bounces right back into my hand. There is some sort of force that the wall is applying back to this tennis ball, so it returns back to my hand at the same velocity. Now, we can say that the momentum that the tennis ball had in the first place was about, we'll call it 0.4 momentum, and it came back with 0.4 momentum. That means the change of momentum was actually 0.8, right? If it comes back at the same velocity, then our change of momentum is 0.8. Now, if the tennis ball is only making contact with the wall for about like a tenth of a second, then that means that the wall is actually applying 8 newtons of force back onto the tennis ball. Think about it like this. The ball coming in with 2 meters per second, bouncing back off with 2 meters per second. It has to bounce off that fast. It needs all that force to return back to its same position with the same velocity. So now I'm going to throw this ball as hard as I can into a bed sheet. And I need you to tell me, do you think the bed sheet is going to apply more or less force than the wall did on the tennis ball? Alright guys, so I'm going to step a little bit out of frame, but I'm going to throw this tennis ball as hard as I can into the sheet. Watch what happens. Here we go. 3, 2, 1. Hopefully you notice that it actually applied less force, and it applied that for 2 reasons, right? First reason was that the tennis ball didn't fire back out at me. It stopped. It went to 0, right? So the velocity went to 0. It wasn't returned at the same velocity. The second reason was, if you watch it again, you can see that the sheet absorbed it. So there's a longer amount of time, right? With our wall, it was only like a tenth of a second. For this one, it was almost a full second. So it took in a lot more force, right? So it has a lot less force on the ball. So, good.